It usually starts with this moment of just perfect, frictionless clarity.
Oh, yeah.
Like you are staring at a screen, looking at a flawless 3D render of a new product.
Yeah.
Or maybe you are hovering over a pristine sketch in a notebook.
Mm-hmm.
And in that space, the idea is completely under your control. It's just perfect,
It's safe.
right? The safe. But then you hit print, or you hand those beautiful blueprints over to a manufacturer, and suddenly reality hits back.
Yeah, it always does.
The 3D printer jams, or the materials warp under the heat, the budget just explodes. That pristine idea crashes headfirst into the messy, the unforgiving physical world.
It is the absolute definition of a reality check. I mean, we spend so much time celebrating the eureka moment, right?
Oh, absolutely.
But the real crucible is that exact an idea is forced to obey the laws of physics and economics.
Yeah, and that collision between a perfect idea and an unforgiving reality is exactly what we are unpacking in our stack of sources today.
It's a great stack today.
It really is. Welcome to this custom-tailored deep dive.
Mm-hmm.
Today's mission is exploring this theme of creativity meets the machine, like what happens when ideas leave the studio.
Right.
We have a truly fascinating stack of material in front of us. It ranges from historical analyses of Victorian computing to academic papers on arts entrepreneurship to MFA theses on creative burnout.
We're covering a lot of ground.
We really are. And even the gritty details of deep tech commercialization.
Yeah.
We're looking at the often invisible work of translation that happens when a concept leaves that protected space of the imagination and has to actually survive the real world.
Yeah, and just setting the stage here, our sources point to a central underlying conflict. The early stages of any design process, whether you are, sculpting, coding, or engineering, they prioritize speed and flexibility.
You want to move fast.
Exactly. Speculative freedom. You want to iterate quickly. But the moment you decide to make that concept real, especially if you want to scale it up, the demands completely flip.
They change entirely.
Right. Mass realization requires strict repeatability, rigorous standardization, hard financial viability.
Yes.
And this creates a profound chasm that both artists and technologists constantly struggle to cross.
Okay, let's unpack this. Because to understand why it is so incredibly hard to make things real today, our sources suggest we actually have to look backward.
Way backward.
Right. We have to understand how humanity historically divorced the act of thinking from the act of making.
Yeah, and this epistemological divide actually traces all the way back to classical antiquity.
Wow, really?
Yeah, if you read Plato's Republic, the social hierarchy is explicitly structured to separate intellectual labor from manual labor.
Oh, interesting.
The disembodied rationality of the philosopher was elevated as the highest form of human achievement, while the practical hands-on knowledge of the artisan was heavily subordinated.
So the maker was seen as lesser.
Exactly. Plato essentially argued that the artisan, the person actually making the physical world function, shouldn't even have the time or social standing to sit around and govern or philosophize.
It's wild to consider that a philosophical bias from thousands of years ago still infects how we view labor today.
It really does. But that philosophical division was fully weaponized centuries later during the Industrial Revolution.
Okay, the factory era.
Right, specifically through Taylorism, which is often called scientific management.
Oh, right.
In a pre-industrial workshop, the craftsperson held all the knowledge in their head and their hands. Taylorism changed that.
How so?
Planner managers deliberately extracted that craft knowledge from the workers on the factory floor. Harry Braverman famously identified this process as de-skilling.
De-skilling, yeah.
The entire goal was to separate conception from execution.
So they basically stole the thinking part of the job.
Precisely. Craft skill ceased to be a resource controlled by the maker. Instead, thinking became the exclusive domain of engineers and managers in an office.
Wow.
And the worker on the floor was reduced to just a pair of hands executing a hyper-specific, repetitive task.
I have to push back on that absolute division, though, because it assumes you can actually divorce the two without losing something vital.
Right.
It's like assuming a Michelin star chef can sit in an office, type out a flawless, world-changing recipe, and hand it to a line cook without ever actually touching a pan.
Right.
Or smelling the ingredients, or feeling the heat of the stove. Doesn't true craft-like, true innovation require the mind and the hand to work together?
You would think so.
I mean, you can't just mandate a perfect physical outcome from a desk, can you?
Well, you are hitting on exactly what design theorist David Pye addresses in our sources.
Okay.
He looked at this separation and divided manufacturing into two distinct modes. First, there's what he calls the workmanship of certainty.
The workmanship of certainty.
Right. That is the ultimate goal of Taylorism and mass production. The quality of the outcome is completely predetermined by automation and machinery before a single item is actually made.
Okay, so it's guaranteed.
Exactly. You press a button, a hydraulic press stamps a sheet of metal, and it is exactly the same every single time.
Highly predictable, highly scalable. The thinking is completely finished before the making even begins.
Precisely. But he contrasts that with the workmanship of risk.
Oh, I like that term.
Yeah. This is where the quality of the final piece depends entirely on the continuous, real-time judgment, care, and dexterity of the maker.
Okay, so it's not automated at all.
No. Think of a wood carver working on a piece of raw timber. Every single pass of the chisel carries the risk of ruining the entire piece.
No way.
The wood might have a hidden knot, or the grain might suddenly change direction.
Right, the material fights back.
It does. The maker has to constantly read the material and adjust their technique on the fly. In workmanship of risk, the thinking and the making are happening simultaneously.
Which makes sense of this modern illusion we are currently living in.
What do you mean?
Well, one of our sources on craft fetishism points out that we currently live in a neo-craft economy.
Oh, right, yes.
We love the aesthetic of the workmanship of risk. We pay a premium for artisanal coffee, heritage denim, small batch craft beer.
Absolutely.
We romanticize the rugged individual maker. But the reality is that many of these craft industries are actually operating on highly automated, Taylorist labor processes.
It's all hidden behind the scenes.
Exactly. They hide an industrial, de-skilled assembly line behind a marketing facade of artisanal authenticity. We want the story of the woodcarver, but economically we rely entirely on the stamping machine.
Which fundamentally alters how modern creators approach their work, because the physical world introduces material resistance, because it forces you into the workmanship of risk, where failure is always one chisel slip away. Many modern creators just retreat into the digital realm.
It's safer there.
The digital world feels so much safer.
And that brings up a really fascinating concept from the philosopher Gaston Bachelard.
Oh, the formal versus material imagination.
Yes. He made this brilliant distinction between the formal imagination and the material imagination. When you are designing on a screen using CAD software or 3D modeling, the formal imagination absolutely thrives.
Because there are no limits.
Right. You are dealing purely with geometry, shapes, and visual imagery because pixels have no density.
No.
They have no weight. They have no friction.
Yeah.
The formal imagination is like playing SimCity. You just drop a massive skyscraper wherever you want with a click of a mouse. It is effortless.
It's a God mode, basically.
It really is.
Yeah.
But the material imagination is actually having to dig the foundation for that skyscraper in a swamp.
That effortlessness of the formal imagination creates a very dangerous illusion, which software developers and hardware engineers refer to as the prototype trap.
The prototype trap.
Yeah. Digital tools heavily optimize for the speed of creation. You can render a beautiful photorealistic product in a single afternoon.
Oh, for sure.
But when you try to force those digital ideas into physical reality, they hit a massive wall of physics.
It doesn't work the same way.
No, it doesn't. Bachelard argued that without the material imagination, where a designer actually understands the density of a material, the strong and weak axes of wood, the specific melting points of plastics abstracting it digitally is a trap.
You lose touch with reality.
Exactly. Without material imagination, you end up with what is called premature innovation.
But this isn't just a modern software problem.
Yeah.
I mean, if you look at history, brilliant minds have been slamming into this exact wall of material resistance for centuries.
Oh, yeah.
The sources bring up Charles Babbage and Ada Lovelace in the Victorian era as the ultimate example of this.
It is the perfect historical mirror. In the 1840s, Ada Lovelace conceptually grasped the first general-purpose computer program.
Which is just mind-blowing.
It really is. She understood that Babbage's proposed analytical engine could manipulate symbols, not just numbers. She saw that it could compose music or process complex logic.
So the idea was sound.
The mathematics were completely right. The theoretical framework was completely sound.
But Babbage's machine completely failed to materialize in his lifetime. And not because the idea was flawed, it was because the physical infrastructure of the Victorian era simply did not exist to support it.
They couldn't build it.
Right. To build the analytical engine, he needed tens of thousands of precisely machined brass and steel gears.
Yeah.
But Victorian machine shops couldn't machine gears to the exact microscopic tolerances required.
And that matters a lot.
Oh, massively. If 1,000 gears are each off by just a fraction of a millimeter, the physical friction compounds, until the machine literally locks up. The physical world of the 1800s could not support the brilliance of the computational idea.
It's tragic, really.
And here's where it gets really interesting.
Yeah.
Because you see this same trap in industrial design, too.
Oh, you mean the Dymaxion car?
Yes. Look at Buckminster Fuller's Dymaxion car in the 1930s. On paper, it was this beautiful, aerodynamic, highly efficient vision of the future. It looked like a Zeppelin on wheels.
A beautiful design.
Yeah, but when they actually built it and drove it, it was physically terrifying. Yeah, the aerodynamic shape that looked so perfect in the formal imagination created massive lift in the real world. At high speeds, the car literally wanted to take off and lift off the ground.
Like an airplane.
Exactly. The auxiliary material technologies, like the advanced suspension and downforce mechanisms, needed to stabilize a shape like that. They just didn't exist yet. Chrysler ultimately abandoned it.
That gap between the perfect blueprint and the disastrous physical test brings us directly to the modern equivalent of this historical failure.
Okay, what is that?
In product development, engineering, and deep tech, this phase is known as the dreaded Valley of Death.
The Valley of Death. Sounds intimidating.
It is.
I feel like if you're listening to this and you've ever tried to launch a physical product on Kickstarter,
Yeah.
or tried to scale up a recipe from feeding 2 people to feeding 200, you have experienced a mini version of this exact friction.
Oh, absolutely.
It's the place where promising ideas just quietly disappear.
In technical literature, the Valley of Death corresponds to technology readiness levels, or TRLs, 4 through 7.
Walk us through what those mean.
Sure. So to give that some context, TRLs 1 through 3 represent basic research.
Okay.
That's the conceptual stage in a controlled laboratory. TRLs 8 and 9 are full commercial deployment, where a product is actively being manufactured and sold.
So 4 through 7 is the gap.
Exactly. The Valley of Death is that missing middle. It is where concepts have to transition from a controlled, successful lab environment to an economically viable, repeatable, mass-manufactured product.
And that's where they die.
Often, yes. And what our sources heavily emphasize is that the failure here is almost never the core science. The science usually works.
Wow. So if the science works, what is the actual mechanism killing these ideas?
It is the invisible, highly complex work of translation. It is the cost of production modeling. It is navigating complex, contradictory regulatory landscapes.
Translation, right?
Think about a brilliant new solid-state battery. It works perfectly on a pristine lab bench at room temperature, but the moment you try to integrate it into a bumpy, freezing, vibrating, real-world electric vehicle chassis, the brittle materials crack.
The real world strikes again.
Exactly. Or think about injection molding. An innovator designs a perfectly functional 90-degree plastic bracket in CAD software.
Oh, sure.
It looks great on screen, but in a mass manufacturing plant, molten plastic won't flow evenly into a sharp 90-degree corner without cooling unevenly and snapping.
So what happens then?
The manufacturing engineer tells the designer they have to curve the edges, but curving the edges changes the physics of the whole device.
Oh, man.
Which requires a total redesign of the internal components, which pushes the launch back a year, which bankrupts the startup.
It's a domino effect.
Exactly. Furthermore, there is a massive lack of secure pilot facilities where innovators can actually test these intermediate scale-up processes without fronting millions of dollars.
That injection molding example perfectly highlights something else the sources bring up. The barriers in the Valley of Death aren't just mechanical or financial.
No, they're not.
They are deeply, stubbornly human. Innovators are incredibly passionate people. They treat their ideas like their children.
They do.
So when a manufacturing engineer demands compromises, like changing that sharp corner to a curved edge to survive mass production, the innovator often gets highly defensive.
They feel attacked.
Yeah. We see profound language and motivation barriers here. Academics and creatives speak in terms of discovery, novelty, and theoretical perfection.
Right.
Manufacturers and production engineers speak in terms of yield rates, unit economics, risk reduction, and supply chain logistics. They are fundamentally speaking entirely different languages while looking at the exact same object.
And trying to constantly translate between those languages while surviving the intense output-driven pressure of commercialization, it takes a massive psychological toll.
It sounds exhausting.
It is. We reviewed Himani Mehta's MFA thesis, which dives deep into the human cost of this grind. The contemporary creative and tech landscape prioritizes extreme speed and visible, measurable worth.
Everything has to be faster.
Right. Mehta points out that this environment reduces the act of creativity to a consumable outcome. You are only as good as the product you just shipped. Creativity ceases to be a reflective, sustaining practice and becomes an extraction industry.
It's the classic exhausting job description we've all seen, right?
Yeah,
Must thrive in a fast-paced environment,
exactly.
which usually just means, must be willing to sacrifice your well-being for our production schedule.
Precisely. Mehta argues that this systemic pressure causes immense creative anxiety. It leads to deep burnout, rampant imposter syndrome, and the slow erosion of a person's creative identity.
That's heartbreaking.
It really is. Often we treat this burnout as a personal failing. We tell people they just couldn't hack it or that burnout is a necessary rite of passage in the startup or art world.
But it's not.
No. Her thesis reframes this burnout as a systemic condition. It is the inevitable result of an industry that demands the frictionless, instant speed of the digital world, but forces human cognition to execute it in the messy, resistant reality of the physical world.
So what does this all mean? If the valley of death is where ideas go to die, partly because of the physical laws of materials, but largely because of siloed thinking, extreme language barriers, and systemic burnout, how do we actually build a bridge across that chasm?
Well, the sources point to a historical blueprint for success, but it requires forcing entirely different disciplines to share the exact same sandbox and confront the material world together.
Okay, what's the example?
The prime example provided is EAT experiments in art and technology.
EAT, this was founded back in 1966, right?
That's right.
But wait, you're telling me they intentionally put avant-garde abstract artists in the exact same room as corporate, highly structured Bell Labs research engineers?
Yes, they did.
That sounds like a recipe for absolute disaster. I mean, how did they even communicate without killing each other?
It was a massive culture clash at first. I mean, EAT was founded by the artist Robert Reichenberg and a Bell Labs engineer named Billy Kluver. The core philosophy was to pair artists and engineers on a strictly equal basis.
So no boss and employee dynamic.
Right. Not as a boss and an employee, but as equal collaborators. They threw them together to see what would happen when the rigid, standardized world of industrial engineering collided directly with the boundless, risk-taking imagination of contemporary art.
I would assume the engineers just ended up acting as glorified technicians, right? Like just building whatever crazy thing the artist demanded.
That is the common assumption, but the reality was a deeply reciprocal two-way street.
Oh, really?
Yeah. The EAT project revealed that artists brought something vital to the lab, a unique sense of scale and a willingness to push materials far beyond their intended safe limits.
They weren't afraid to break things.
Exactly. But most importantly, the artists brought a profound sense of personal responsibility for the final outcome.
What do you mean by that?
Well, an engineer in a corporate lab might say, well, material failed at this threshold, and my boss said the deadline was Tuesday, so we're stopping here.
Right. Good enough.
But to an artist, the artwork is a direct reflection of their personal identity. They don't clock out.
Ah, I see.
That level of uncompromising ownership and willingness to engage in the workmanship of risk profoundly influenced the engineers. It taught them to look past standard tolerances.
Wow, so the engineers learned to take more risks.
Yes. And in return, the engineers gave the artists a vast new palette of cutting-edge mediums, things like wireless telemetry, Doppler sonar, synthetic materials.
Things the artists would never have access to otherwise.
Exactly. And they brought highly pragmatic problem-solving skills to ground the artists' wilder concepts.
That is such a powerful dynamic, and it connects perfectly to how some of our sources are trying to rethink modern education to bridge this gap today. There's a fascinating paper in our stack by Callender and Cummings about teaching what they call productive deviance.
Productive deviance is a brilliant term for this.
Isn't it? They argue that to cross the chasm from concept to reality, we need artists who don't reflexively view commercialization, scale, and business as some evil sellout of their values. And simultaneously, we need business founders, scientists, and engineers who don't view art as just a superficial design wrapper.
Yes, exactly.
You know, a pretty coat of paint you slap on a product at the very end to make it marketable. To truly collaborate in the valley of death, both sides have to learn to deviate from their institutional norms.
Has to get uncomfortable.
Yeah. You have to step out of their comfortable silos, get comfortable with the apparent absurdity of the other side's process, and actually respect the different types of intelligence they both bring to the table.
This raises a very important lingering question, though.
Okay, what's that?
If we look at the historical data, and we know that cross-disciplinary collaboration like EAT works, and we know that engaging with the workmanship of risk is essential for true material innovation,
Right.
Why do so many incredible ideas still fail to scale up today?
I think it's because knowing the path isn't the same thing as having the bridge built for you.
That's a good point.
We can teach all the productive deviance we want in universities. But if a deep tech innovator doesn't have a physical pilot facility to test their prototypes, or if a designer doesn't have the patient capital required to survive the messy, expensive middle of the valley of death, the idea still dies on the lab bench.
It needs support.
Yeah, the friction of the real world isn't the enemy of the idea. It is the crucible that actually gives the idea its value. But you have to be able to survive the crucible.
Exactly. So, bringing our deep dive together today, we've seen that a successful idea doesn't just survive the arduous journey from the studio to the real world by accident.
No, it takes work.
It requires a deep material imagination to understand and respect the physical constraints of the world, rather than just abstracting them away on a screen.
Right.
It requires the courage to engage in the workmanship of risk, where failure is not just possible, but likely.
Very likely.
And perhaps most critically, it requires the humility to collaborate across massive disciplinary divides, learning to speak different languages to translate a fragile concept into a durable reality.
Which leaves us with a larger landscape to consider. We've talked about the historical gaps from Plato to Taylorism, the psychological toll of burnout, and the collaborative solutions of the 1960s.
We've covered a lot.
But looking at our current environment, what infrastructure, what specific skills, or what new stages of development might need to exist for more ideas to successfully complete this journey?
That's the big question.
If the Valley of Death is a systemic failure of translation, the bridges we built across it must be systemic as well. It is a territory we will definitely have to continue exploring.
And as we navigate that territory, the nature of how we generate those initial ideas is shifting dramatically.
And here's a final provocative thought for you to mull over as we wrap up today. We started this deep dive by talking about the seductive perfection of the digital screen and the illusion of the formal imagination.
Right.
Today, we are relying more heavily than ever on generative AI and massive digital abstraction to do our thinking for us.
We really are.
As those digital tools become infinitely faster and more frictionless, will we lose our material connection to the physical world entirely? Will we become entirely separated from the heat of the stove, the resistance of the metal, and the grain of the wood?
It's entirely possible.
Or will this new wave of frictionless technology finally force us to rebel, pushing us to redefine what it means to truly craft something with our own hands in the physical realm?
I wonder.
The next time you look at a pristine, flawless digital render on your screen, ask yourself, what is it actually going to cost to make this real? Thanks for joining us on this deep dive.